that is OC and SC test once again. Example problems. So let me first review what we had done in the last class. So I'm just sharing the screen of equivalent circuit of the transformer, and then on your screen you can see a complete transformer is represented by 4 parameters. So that is R0, X0, R01 and X01. So to determine R0 and X0, which is we use OC test, and to determine R01 and X01, we use the short circuit test. So total 4 parameters we are able to get using these 2 tests. And this is how the open circuit test is conducted. Typically the high voltage side is left open, and on the low voltage side we connect the 3 instruments. One instrument is voltmeter, one instrument is wattmeter, and another instrument is the ammeter. So the voltage, we apply full rated voltage to the primary winding. So first check whether the experiment is correct or not is first you look at the voltage level, and then if the rated voltage is matching with the LV voltage, then it is correct. Then you take the noting of the no load current and no load input power, whereas the secondary is open. Now how does it look like in the equivalent circuit? In the equivalent circuit, here I2 dash will be 0. That means the current flowing through R01 and X01 is 0. So practically this part, there's no voltage drop, there's no role played by this entire particular branch. So you can actually simplify the circuit and only look at this part, that is R0 X0 connected in parallel across V1. So therefore directly I can first of all, given the rating of P0, I can find out what is IW. So IW is, so I think here are the formulas. So first from this you find out the IW. IW is I0 cos phi, which is nothing but P0 by V1. And then once you get IW, you find out I mu, and then through them you can find out X0 and R0. Then coming to the short circuit test, here now the connections are reversed. The low voltage side is short circuited, whereas the high voltage side is meters are connected in that. So here you should apply reduced voltage. You cannot apply full voltage because the secondary side is short circuited, which results in very high current. You apply reduced voltage and gradually increase the voltage such that the current in the ammeter is equal to the rated current of the machine. So if the rated current is flowing in primary, the rated current will also flow in the secondary winding. That means both rated currents are flowing. That means I will cover entire copper loss aspect into this. Whereas they are dependent on the reduced voltage, so therefore the amount of current flowing in that is negligible. So we can neglect that. So here I have 3 readings again: the reduced voltage, the rated current, and the wattmeter, that is measuring the copper losses. So again, this is a very simple circuit. So here I1 square R01 is P1. So from that directly I can find what is R01, and impedance Z01 we can find by V1 and I1, and through that I can find the X01. So after knowing that theory, so we had now come to an example problem, that is, given the OC test and SC test, we solved a problem where we have to find out the parameters of machine. So how did we find the parameters? R0, X0, R01 and X01. So for that, first calculation is that of finding the power factor cos phi, then find the working component of the current, then find the resistance and reactant and the magnetizing component. So these are the calculations that are there. So ultimately from this we find the resistance value here and the reactance value here, that is on no load. So after that, we take the SC test. Given the data of the SC test, again I can repeat this simple calculation that we saw before, and finally find the R0. So since the SC test has been done by keeping the measurements on the high voltage side, what you actually get is R02 and Z02. So that's why we are getting this one. And ultimately, again, we have to convert them back and find out the R01 and X01. And finally, we build the complete equivalent circuit as shown in the diagram here. So this was one problem we solved. We have solved one more problem also. Let me now share that problem. The same process we followed to find out what is R0, what is X0, and then from the SC test again we find R0 and X0. And then the complete equivalent circuit we have built here. Now not only that, we can also determine what is the voltage drop. So you know this formula of voltage drop. Through that we also determine the voltage drop. And in fact, we've done one more, I didn't realize this, we have done one more problem again the same way, given the, this is the reverse actually. Given the parameters, we have found, we have tried to estimate the results of the OC test and AC test. So this is the reverse way. So this also we have done. So results of AC test is here, and this is the results of the AC test. And whereas the results of OC test is here. So this way we are able to do that. So you have any doubts on this topic? So please take a minute. If you have any doubts on OC test or AC test, please let me know. Let's jump to today's class. Today what I want to talk about condition for maximum efficiency. So if you look at the transformer, what is the condition for maximum efficiency of the transformer? So if you look at the transformer equivalent circuit, the transformer equivalent circuit looks something like this. You have the primary side. In the primary side, there is a resistance and there is a reactance. So this is R0 and this is X0. And then I refer everything to the primary side. So this is totally R01 and this is X01. So I have referred both resistance of primary and secondary to primary side, and both reactances also I have referred. Now here I have V2 dash and this current is I2 dash. So the dash notation here represents that there is ideal transformer, but then I have transformed their values to primary side and then I am showing here. Here I have connected the source. So if you notice, so the source is nothing but V1. So if you notice, let me also connect the load here first. And here the load is connected. So now initially if the load is 0, then I2 current is 0. And then this branch, irrespective of the level of the load may be 0 or load may be full load. All the time the current that is flowing here will be constant. So this current I naught is present all the time. This current is IW, as you know, and this current is I mu. So this is a separate parallel branch, as you can see. So these losses are always constant. Okay. So this is iron losses are always constant. Of course, this is subject to rated when rated voltage is applied. So let's denote this as Wi. This is the iron losses. So Wi represents the iron losses. Now coming to copper losses. Now what is the current here? This current is I2 dash. And this current is I1. Now here we make a small assumption that this I1 current is actually flowing in R01 and X01, not I2 dash. So the copper loss depends on the load. So load is variable. So copper loss is variable. Is also variable. So let's denote it by a symbol WCU. So we have two losses. Wi is the loss, iron loss. WCU is the copper loss. So what is the value of WCU? So WCU is nothing but I2 dash square multiplied by R01. Or I can assume that the copper loss, just a minute, I got a call. The copper loss is I1 square R01. So because the difference between I1 dash and I2 dash is not that, I1 and I2 dash is not that high, only I naught is there. So now we have total losses is nothing but iron loss plus copper loss, which is nothing but iron loss, which is constant, plus copper loss, which is variable, depends on the amount of current I1. Now what is the efficiency? So when you say efficiency is nothing but output by input. So this is the efficiency of the transformer. Now what I want to do, the plan is to find out what is the efficiency, and then I can based on that I can find the maximization of efficiency. Now this I can also write, efficiency is output by input. I can also write input minus losses divided by input. So I can also write like this. In the place of output, I am writing input minus losses. So what is the input for the transformer? Now if I go back here in the diagram, so the input of the transformer is V1 I1 cos of phi 1. So that is the input of the transformer. So I'll get V1 I1 cos of phi 1 is the input of the transformer. Minus what are my losses? Losses are Wi minus I1 square or not 1, and then divided by again the input, that is V1 I1 cos of phi 1. So like this I am getting the input. Now I can further simplify this. So this is nothing but efficiency is equal to, this is 1 minus iron losses divided by V1 I1 cos of phi 1 plus, so this minus into minus will become plus I1 square R naught 1 divided by V1 I1 cos of phi 1. Now if I differentiate both sides, with respect to I1, what will I get? So I'll get differentiation of efficiency with respect to I1 will be, so differentiation of 1 is 0, and here I1 is in the denominator. So because I1 is in the denominator, so I'll get minus Wi by, so this minus will become plus, then it will be V1 I1 square cos of phi 1. So differentiation of 1 by x is minus 1 by x square. So you had know that from the basics of this topic. Next, what is the differentiation of this one? So here I1 is in the numerator, because I1 and I1 I can get cancelled. So whatever is left out is nothing but plus R naught 1 divided by V1 cos of phi 1. So I'm sorry, I think I made a mistake. Actually this is plus here. So if this is plus, then here it is minus sign. I made a mistake with and then when you differentiate, so here you will get minus sign. Okay, now it is correct. So just make a small correction. Now from this, if I, so this whole differentiation should equate to 0. Now from this I'll say this is Wi by V1 I1 square cos phi 1 should be equal to R naught 1 by V1 cos of phi 1. So this is the condition for maximum efficiency. So in this condition, you can see I can cancel off V1 on both sides. I can cancel off cos phi 1 on both sides. So therefore, what is remaining is I1 square equal to Wi by R naught 1, and this implies I1 equal to square root of Wi by R naught 1. So this is one thing. Or you can also, this also implies R naught I1 square R naught 1 equal to Wi. So this is nothing but copper losses. So maximum efficiency is achieved when copper loss equal to iron loss. So this is a very important observation. So for that value of I1 where the copper loss and iron loss are equal, then we achieve the maximum efficiency. So let's work out a problem on this. So any doubts on this? So from this we also get one more point, that is, so let's see, condition for maximum efficiency is iron loss should be equal to copper loss. That means I1 square or not 1. Now, what is the copper loss under full load? So let WCFL is nothing but full load copper loss. So now if I divide full load copper loss on both sides, WC full load, WC full load. So I am dividing both sides of the equation with that copper loss full load like this. But what is copper loss at full load? You say WI is anyway constant. WC at full load is equal to I1 square or not 1 divided by I1 full load. So this is the full load current multiplied by R01. So here I can cancel out like this, the R01. Then here you can see the fraction. That means if I square root both sides, square root of Wi by Wc full load is equal to I1 by I1 full load. That means at what fraction of full load current we are getting, that we can find out. So at what fraction of the current out of the full load current will the efficiency be maximum can be determined like this. So this is fraction. Now what you can do is again bring I can multiply both sides. I can multiply full load rating. That means V1 I1 full load cos of V1 I1 full load is equal to, so if I multiply it on both sides, so let me do like this. Full load multiplied by square root of Wi into Wc full load is equal to full load. So full load measured in kVA. So I1 by I1 full load I'll get. So whereas this quantity is nothing but V1 into I full load multiplied by Wi by Wc full load is equal to this also V1 into I full load I1 by I1 full load. So here these two will get cancelled. So V1 I1 is nothing but the load, amount of load, and this one V1 IFL is the full load. So fraction of load at which efficiency is maximum is, so that is nothing but V1 I1, so that is nothing but full load multiplied by square root of iron loss by copper loss. So this will tell you at what fraction the efficiency is maximum. So this is another important formula we can use. To understand this further, so this is example 20-1. Transformer has core loss Wi equal to 1.4 kilowatts and full load copper loss is 1.6 kilowatt. So find at what kVA load is the efficiency maximum. So this is the first thing we have to find. And the second one, efficiency at half full load .8 power factor leading. So this is the question. Okay. So take a minute, note down the question first and try to solve the question yourself. I'll give you 2 minutes time. Try to solve the question, and meanwhile I will also solve it. So the equation is like this. So just now we had derived that. That means load at which efficiency is maximum is full load multiplied by square root of iron loss by copper loss. So that is nothing but what is the full load? Now look at the kVA of the machine, 150 kVA. So you go back here, I can substitute 150 kVA multiplied by iron loss is 1.4 kilowatt and copper loss under full load is 1.6 kilowatt. So now I have this. So here kilowatts I can cancel out. Then I have, let me use calculator to find this. Multiplied by square root of 1.4 divided by 1.6. So I'm getting 140.3 kVA. So when the load is 140.3 kVA, at that value, the efficiency will become maximum. So that is what is the what we are getting here. The next one, efficiency at half full load, 0.8 power factor leading. Now, so what is efficiency? So how to find? Efficiency is nothing but output by input. There is nothing but output by input minus losses. So now I want what is the output? Okay, at half full load, 0.8 power factor lead, output equal to. So what is the full load kVA rating? 150 kVA. So this is multiplied by half and this is multiplied by 0.8. The power factor if I multiply. So then this will be 75 kVA multiplied by 0.8. That will be 60 kilowatts. So this will be the output. Now what is the iron losses? Iron loss is nothing but 1.4 kilowatt, that is given in the data. Now at half full load, so first of all copper loss. One-fourth. So what is happening is the copper loss is proportional to, so why? So the copper loss proportional to current square. So since copper loss is proportional to square of the current, if the current is becoming half, then the copper loss will become 1/4. So therefore, uh, copper loss at half full load is equal to 1.6 divided by 4. So that will be 0.4 kilowatts. So therefore, efficiency will be nothing but output is 60 kilowatt divided by 60 kilowatt minus 1.6 kilowatt, sorry, 1.4 kilowatts minus 0.4 kilowatts. So this is the total efficiency. So that will be nothing but if I quickly use my calculator again. Oh, I'm sorry, this is output plus losses. So I have to add here. So 60 divided by 61.8. So this is the efficiency of the transformer, 97.08%. So again, I hope you understood this problem. Just take a minute, go through the solution. If you have any doubts, feel free to ask. Just take 20.2. Draw a curve with efficiency on y-axis and fraction of load on x-axis for following transformer. So the following transformer data is like this. The transformer rating is 120 kVA and it is 10,000 volts divided by 2000 volt step down transformer. So whose iron loss is 2 kilowatt. Full load copper loss. So this is nothing but Wi. So full load copper loss is, let's say, 4.2 kilowatts. So copper loss at full load. So what I want is, I want to plot like this, where on y-axis I have the efficiency and on the x-axis I have the load. So this is the fraction of load. So 1 represents the full load. And then I can 0 represents the no load. So the efficiency of course 0. So assume power factor equal to 0.8 lag. Okay. So I want to get the data something like this. So how will you do that? So obviously, because if you want to draw a curve, very task. So let's come to the solution of this particular problem. So obviously, we'll try to solve it by writing a small code. So based on following equations. Okay, so now what is the, let x be the fraction of load. So if x is the fraction of load, so what is the output? Output is nothing but full load kVA multiplied by x multiplied by power factor. So because output should be in active power, so if I multiply by power factor and multiply by the fraction of load and the full load kVA, then I'll get the output. So this is the first equation we'll try to implement in the program. Now what is iron loss? Iron loss is Wi, so this is nothing but constant. Next we have copper loss. So as I told earlier, the copper loss is, so this is copper loss at full load. Is nothing but WCUFL. So this is the notation I am doing. So copper loss at full load, let me represent it as WCUFL, full load. Now copper loss at fraction X. So how do I get? So is nothing but, is not, because the copper loss is proportional to the square of the current, the copper loss will be proportional to the square of the fraction again. So X square copper loss at full load. So therefore efficiency will be equal to full load kVA, that is, let me write in this form, output by output plus losses, that is iron loss plus copper loss. So the what I can do simply is efficiency is nothing but X into full load kVA into power factor divided by, again the same thing will repeat, output is same, so X into full load kVA multiplied by power factor plus iron loss is constant plus X square into WCU full load. So like this I can get the full load copper loss. So this is a one single equation, and everything is available in this equation. We just have to draw the plot. Okay. So here I have derived so that efficiency is a function of X. So X is a fraction of the load. So I have to substitute X in the numerator and denominator. Rest everything is a constant. So let's do that. So this is the main formula. So how we'll implement this formula in MATLAB? So let me go to my MATLAB screen and then I'll try to share it. So on your screen, now you are able to see this particular area. So in the middle, I can now write the program and I can execute the program, and the results of the program I can see on the right side. So let me write the program first. So it is very straightforward. Nothing is complicated here. So what is a full load kVA? See, full load kVA I already know. I'm just writing the given data. Full load kVA is 120. In fact, I'll just write kVA equal to 120. Then iron loss W 2 kilowatts. Then copper loss WCU FL. Full load copper loss equal to 4.2 kilowatts. So this is unit is in kilowatts. And then power factor PF equal to 0.8. So just based on this, I can define efficiency EFF equal to X multiplied by, so first let's define X. So X is nothing but 0 to 1 in the steps of 0.1. So this is a syntax. If I write like this 0 colon 0.1 colon 1, X will be considered as a vector and different values of X will be there. So let me just show you that. So if I run this, so on the right hand side, you can see the variables are being defined, and then the variable X is nothing but you are getting these numbers. So on the right hand side, you can see 0, 0.1, 0.2, 0.3, 0.4 like that. At different values of load, I can find what is the efficiency. Now efficiency is nothing but X into full load kVA divided by X into full load kVA. Of course, into power factor also is there. Plus iron losses plus copper losses. But the copper losses will be multiplied by X square. Like this. So once I solve this equation, so then I will be able to get the value of X. So here I have to use dot star. So I'm getting the efficiency curve. So now plotting it. So let me execute it and see. So I can also give some notation. So just I'm defining the line width and then the line style for the plot. So now I think the result is not displayed fully on the screen. Now you can see on the screen, so the efficiency reaches some maximum value and then it starts decreasing. So this is the efficiency versus the load curve. So on the x-axis you can see is the ratio of the load and on the y-axis is the efficiency. So of course here you cannot see that it is going properly to maximum and minimum. So I'll try to adjust the range. So what I'll do is instead of taking the starting from 0, I'll start from 0.3, 30% to full load. Now if I run, so now you can see clearly at 30% efficiency is below 92.5% and then at 40% efficiency is 93.5. So I hope you are able to see this clearly. At 50% load, efficiency is 94% increasing. At 60% it is slightly higher. At 70% it is even higher. Maximum it is reaching. Then again the efficiency starts reducing. So, and if I increase further, so if I go up to 1.5, you see the efficiency is further dropping if I overload a transformer. So the point or the interesting concept that you should know here is the transformer designed to operate at a particular amount of load. If the load keeps on varying, then the efficiency also reduces. So if you maintain at a particular load level, the efficiency will be maximum, losses will be minimum. So it is advisable to operate the transformer at a particular optimum level of load. So any doubts regarding this? So you can see both, you can see the program on the left side and the result on the right side. Just to go through the program also and then result also. You have any doubts, feel free to ask. Okay, so one doubt one can get is what happens if the power factor changes? So instead of So this is efficiency with power factor 0.8, and then I'll take power factor of 0.9. So I'm defining PF1 and PF2. So one power factor is 0.8, another power factor is 0.9, and another power factor I will define PF3, that is 1.0, unity power factor. So three different levels of power factors I am assuming. So for the first EF1, I'll use PF1. So I'll calculate three efficiency curves. Efficiency curve 2, I'll use power factor 2. And similarly, efficiency curve 3, so I'll use power factor 3. Okay, so now I have three different efficiencies. So for plotting purpose, so first I'll plot one, then there is a command called hold on, then I'll plot the next one. So to differentiate, I'll use different color. So maybe red color and green color maybe for the, or black color. So hopefully if there are no errors in the program, you'll be able to see this one. Yes, I think now you're able to see the result. So now you are able to see the blue colored line is the efficiency with 0.8 power factor. The red color line efficiency with 0.9 power factor, and then the black color line is efficiency with unity power factor. So you can see as the power factor improves, the efficiency of the transformer is also improving. So it is good to operate the transformer at a higher power factor instead of operating transformer at a lower power factor. So that is another interesting point that you can get from this particular graph. As the efficiency, as the power factor improves, efficiency also improves. So again, any doubts on this? Bit late. I thought I'll just talk about one more small concept, and then I'll come back to our, like I'll take 10 more minutes time because we started a little bit late. So finally, what are, so so let's say efficiency on the, I'll just take 5 more minutes and cover the last topic for today, that is all day efficiency. So the load on the transformer not always constant. So if you calculate efficiency 90%, sometimes the load reduces, then efficiency reduces, load increases, then efficiency increases. So all these changes are happening in the efficiency. So efficiency all day. So this is nothing but efficiency all day equal to, instead of output power, I will write output energy in a day divided by input energy in a day. So if you know this, then you can calculate the all day efficiency instead of calculating based on a particular time. So let's do a quick problem on this. So example 20.3, I believe. So find all day efficiency. And the data of the transformer is like this. 500 kVA, iron loss is 3.5 kilowatts, copper loss at full load is 4.5 kilowatt. So number of hours. So out of total day, 6 hours, 10 hours, 4 hours and 4 hours. So if I add all these things, so 10 plus 4 is 14 plus 6 is 20, 20 plus 4 is 24 hours. So 24 hours is one day. So out of that, under 6 hours, the load in kilowatt. So what is the load in kilowatt? 400. Remaining 10, 300. Remaining 4 is 100 kilowatts. And last 4 hours, the load is 0. So this is the load. And then the power factor. So power factor is 0.8, 0.75, and then 0.8 again. And here power factor is not defined. So given this data, how do you find what is the load? I think to solve this problem, let's quickly go to Excel. Instead of MATLAB, I think the better interface to solve this problem is Excel. So I'll quickly and then load in kilowatts. So load in kilowatt is 400, then 300, then 100 and 0. I'm just writing the same data once again. And then power factor. Power factor 0.8, 0.75, 0.8, and power factor is 0 here, not required. So then what is the load in kVA? So the load in kVA will be total load divided by power factor. So then here I'll assume it is 1. So here I'm getting the load in kVA. Now here fraction of load. So fraction of load is nothing but our X. This is fraction of load. So this is nothing but this divided by 500. So here I am getting the fraction of load. Also, what is the copper losses? I can find out the efficiency. So efficiency is nothing but output divided by output plus losses. So the iron loss already defined as 3.5 kilowatts plus copper loss will be nothing but square of x multiplied by 4.5 kilowatts. So this way 98% efficiency. Oh, by the way, I should not use this formula. This is instantaneous efficiency. I think let me delete this. So first I have to find out the copper loss. So copper loss will be nothing but x square multiplied by 4.5 kilowatts. So 4.5 kilowatts like this. This is in kilowatts. Here copper loss energy kWh. So what is the total energy of copper loss? Nothing but copper loss multiplied by the time. So time is 6 hours. So like this 27 units like this. These are all kilowatt hours that is being lost. So let me make some place. So now I got the copper loss. So what is the total copper loss? Is nothing but sum of all the above. So this is total copper loss. Total iron loss in terms of energy. So this is in kWh. So kWh. So total iron loss in terms of this one will be nothing but 3.5 multiplied by 24. So that is 84. So then what is the total output in kWh? So that is nothing but load multiplied by the number of hours. So like this I am getting. So here also I will be getting the total load. So now finally I can find out the efficiency, all day efficiency. So all day efficiency will be 5800 divided by again 5800 plus energy lost in the copper plus energy lost in the iron. So this way 97.62% all day efficiency I am getting. So this way we can calculate the all day efficiency. Because we are running out of time, I solved it very quickly, but then if you look at this sheet slowly, if you go through it, you will also get the idea how to do it. So this is the concept of all day efficiency. So with this I'll end today's class. We'll meet for the next class next Tuesday.